Okay guys, this is the third in a series of lectures on field effect transistors. The first transistors we actually looked at were the JFETs. These guys we have N channel, P channel. These guys, and these are our two symbols. We operate these transistors in what we call the depletion mode. So what we do is we reverse bias the drain, we reverse bias the gate to source, which causes the channel to get smaller. So all your JFETs, we reverse bias the gate to source. Which makes the channel smaller. So that means these guys operate in the depletion mode. So all JFETs operate in the depletion mode. So if we have a N channel, what we do on the N channel, of course, reviewing again, the arrow points toward the N, just like on bipolar transistors. So this is pointing towards the channel. This is the channel. So this is an N channel JFET. Here the arrow is pointing away from the channel. So this is a P channel. What we do is, of course, we get another characteristics is we get maximum drain current. So the drain current is maximum when the voltage gate to source is equal to 0. And we'll never let it go forward bias. Never forward bias. So when it's 0, we get maximum drain current, which means we get maximum source current. Now remember, on FETs, your drain current and your source current are exactly equal to each other because it flows through a channel. And there's no current flow, or just the only thing we have between the base, between the gate lead is leakage current, which is small, so small that we can't measure. So what that means is, if this is an N channel, then what we're going to do is we're going to make the gate to source voltage negative because it's working against the P, right? Because the channel's in. And if we're working with a P channel, what we'll do is we'll make the voltage gate to source positive, which is going to reduce the size of the channel, which is going to make the output current or the drain current go down. So that's what we do when we operate at FET in the depletion mode. It means your gate to source voltage decreases the size of the channel, or it creates a depletion region, which we talked about on P-N junctions. This is talked about the characteristics curves, the drain characteristics curves. Looked at a couple of common source. We looked at common. So this is still a common source. I'll just go put those. This is a common source. This would be a common source. Input on the gate, output. So this would be a common source. We look at input on the gate, output on the drain. So that means the source has to be common. This is a common gate. We input on the source, output on the drain. So this is a common gate. Here, this is a common drain. We input on the gate, we output on the source, so it's common drain. And that's what I've told y'all. The trick is to identify where the input signal comes from, identify where the output signal is taken off of, and the other symbol, the other lead has to be the common. So you got to be real careful when we talk about common, because that's a common to the circuit, but we're talking about the common to the AC signal, not the DC. We looked at using a common source to amplify a microphone. We looked at a common drain. Let's look at this. Looked at a common source that would be used for meter testing. And we looked at the reason. We looked at a common, this is a common drain. used to drive the base of a bipolar transistor. We talked about some of the advantages of FETs, and then we moved into our metal oxide semiconductor field effect transistors, which we refer to as MOSFET. The first MOSFET we looked at was what we called an enhancement mode MOSFET, which means we have absolutely no channel until we put a gate potential there. As soon as we put a gate potential there, it creates an electrostatic field which comes in and pulls electrons into the channel. Of course, what we have to do to operate this in the enhancement mode, remember on the depletion mode, we made, if it's an N channel, we made the gate negative in respect. Here, to operate in enhancement mode, we're going to make this thing positive. Now, positive is electrostatic field, and what does electrostatic field do to electrons? Well, electrons are negative, and we know that opposites attract. So what's going to happen is when we put that negative field on, that positive field on the gate, it's going to attract electrons into the channel. And as soon as you hit what we call the threshold voltage, then we complete the channel, and then we can enhance the channel above that. These are really used a lot as switches. They work really, really great as switches. So as long as they're below the threshold voltage, these things cut off. Once they get above the threshold voltage, these turn on. So we use these a lot in semiconductors that use metal oxide or MOS devices. This is another thing showing that. Okay. And we talked about what the enhancement mode is. So the enhancement mode means we make the channel bigger. Of course, here the enhancement mode means we actually create the channel to make it bigger. So this guy here does not have a channel. There is no place for the current to flow until you exceed that threshold voltage on the gate, and that's what they're showing us here, okay, which creates a positive polarity right there, which does what? Attracts these electrons in here, right? You understand? And then sooner or later we're going to do what? We're going to increase. We're going to create the channel. As soon as we have channel, we have current flow. This is the symbol for enhancement mode MOSFET. EFET. We call them an E MOSFET. And the depletion mode. Now, what we do on the depletion mode is it's very similar, but they don't show this real well. Is what we do on the depletion mode is we have a channel. So this is called a D MOSFET for the depletion mode MOSFET. And y'all know on the next test you're going to have to identify and label all these symbols. So a D MOSFET. So what we do is we have a physical conducting MOSFET. So now these guys are a little bit confusing because since there is no connection, we have no p-n junction. So what would happen if we came over here and we made the gate negative? Well, if you made the gate negative, electrons are negative, what it would do is it would repel them, and it would come over here and would start making the channel smaller, which is what we call the depletion mode. But what would happen if we came over here and made the gate positive? Now, on a JFET, on an N-channel JFET, this would be bad because we have a p-n junction. So if we make the gate positive, and then we have the source negative, then of course now we have a forward bias junction because we have a junction. But between this one and the gate, we have this polysilicon or this silicon oxide insulating layer right here. So what happens if you make it positive? Well, if you make it positive, it's going to come in, it's going to pull more electrons into the channel, and it's going to make the channel bigger. So the channel is going to start spreading out, right? Well, if the channel gets bigger, then the conduction of the FET goes down. The opposition of the channel goes down, which means we have more current flow. So this is the name is what's confusing, not the operation of the MOSFET. We call these depletion mode MOSFETs, D MOSFETs. But actually, they operate into what? Depletion mode, but we can also operate them in enhancement mode. So DMOSFETs can operate either in the depletion mode or they can operate in the enhancement mode. And they don't call them depletion enhancement mode MOSFETs. They call them DMOSFETs. That's what they're called. Believe me, I know. So the book is kind of misleading here. Well, the book's not misleading. This is what they do, but this is what we call them, DMOSFETs. And that stands for depletion mode MOSFETs, but we can actually operate a depletion mode MOSFET in both enhanced and depletion mode, which means really neat. So what I could do now is I could do it a lot. And so here's the symbol for a depletion mode MOSFET. Let's get over there. This is the enhancement. Let's see. They don't show us. In fact, it's actually the first symbol back here. So this is the symbol for a depletion mode MOSFET right here. DMOSFET right there. So what we do is basically the same, but the EMOSFET shows the channel being broken, where the DMOSFET uses exactly the same symbol. Exactly the same symbol. But what we end up with, let me find, let's see, I got it on white. So what we do is we come over here, we have the gate, and sometimes it's drawn like this, sometimes it's drawn in the side. And then we come over here and we have our channel. We have the two sides, and then they identify the channel right here. And then normally, if they bring out the substrate, they'll bring this one out. But normally what they do is they come on internally and connect the substrate to the substrate to the source. And this is usually done internal. And what we can do over here is we use one resistor to bias it. And then we come over here and we would put a common source. We'd put a resistor here and we'd put a resistor there. We don't even need a coupling capacitor on this guy. If I take my output right here, then it's going to be a common source. We can bring AC directly into it. So when this goes up, right, it enhances the channel, which causes the resistance to go down, so the output would go down. And then when it goes down, it would deplete the channel, which would cause the output to go up because we're taking it across. So what we don't even need a coupling capacitor on this guy. We can bring AC directly into it because it operates on the enhancement and depletion mode. We never actually forward bias this junction or reverse bias this junction because there is no junction. Hopefully that makes sense. There is no junction. So this is a lot simpler amplifier as far as biasing, very easy to bias. It's almost got infinite input resistance. All we have is a leakage current, kind of like we have in an electrolytic capacitor, which is too small for us to measure. We can set our input impedance with a resistor right here to whatever Z I want. Normally this guy is going to run a high impedance source into a lower impedance load. And that's just basically what they do. Used a lot. These guys are used a lot. JFETs are used a lot. They're the cheaper of the two. They're a lot easier to make. Your MOSFETs are a little more expensive. They're harder to make because we have to put that insulating layer in here, that silicon oxide layer in here. Got to get that guy in there. So they're a little more expensive to make. This guy here can be used as a nice audio amplifier. This guy, the enhancement mode MOSFET, is used primarily as a switch. The JFET is used for an extremely high input impedance, which means it's not going to load hardly anything down. All these guys have extremely high input impedance, except for the common gate. The common gate has a oops, wrong way, Rich. The source would be on the other side. So the source would be over here. So a common gate, we connect this to common. We bring our input straight in here. We bring our output over here. We have an input resistor right here. We'd have an output resistor right there. This would be a common gate using a DMOSFET. So guys, that's our FETs. So what do we have? Let me escape this, and I'll pause the lecture for a second. What's our FETs? What is our FETs? Of course, FET stands for field effect transistor. We have our JFETs. Sorry guys. We have our JFETs. Let me get my marker back up. It looks like it's on something else. So we have our JFETs, right? These guys operate in the depletion mode. We have an N channel and a P channel. We have our E MOSFETs. There should be a dash right here. These operate in the enhancement mode. And of course we have an N channel. And we have a P channel. Then we have the D MOSFETs. These guys operate in the depletion mode. And they also operate in the enhancement mode. And of course we have an N channel. And we have a P channel. We hook them up in basically the same arrangements that we hook up our bipolar transistors. So we can hook them up common source. We can hook them up common gate. And we can hook them up common drain. JFETs, we use these guys as switches. But remember, we have to reverse bias these guys. eMOSFET, these are primarily used as switches real well. So just about all your microprocessors that runs off MOS run off these guys. DMOSFET, these are our audio amplifiers. But what advantage of these guys is that they have an extremely high input impedance. The biggest disadvantage, of course, is they're limited on the amount of power they can conserve or use. Another problem we have, especially when we get into MOSFETs, that we really need to talk about is what we have is this insulating layer right here. This guy right here is extremely thin. It is extremely thin. So what happens if we get a static discharge through this thing and it punctures a hole through that polysilicon or the silicon oxide, then now we've just damaged our FET. So the problem with MOSFETs is that they're susceptible to damage for static electricity. So we got to handle these things carefully. And the problem is you might punch a little tiny hole through there and it don't show up instantly, but then later on it kind of cascades. When current flows through there, it starts getting a little hot, then causes the silicon layer or the oxide layer to break down a little more, and then over time it goes bad. So we take extra precautions, and like I said, y'all remind me when we come back on Monday, because that's a pretty good way off, to show y'all some of our static wristbands, our static mats, show y'all some static bags and some static foams that we would use when we started playing around with these MOSFETs. Now JFETs, we don't have the problem. because it does not have that real thin layer. But when you get into these MOSFETs, and a lot of people just call this MOS, by the way. So if you ever hear the term MOS, it's made out of MOS. They're talking about MOS FETs. And of course, all the memory in your computer is MOS, so you need to be really careful if you work inside a desktop computer to make sure you guard against static discharge. And we'll show you that on Tuesday if you're reminded. The last thing we're going to talk about is one of the things that's becoming very, very popular. And in the field of electrical drives or motor drives, there's always been a desire for years to be able to control the speed of a motor. Control the speed of a motor. Now, one of the advantages of a DC motor, one of the big advantages of the DC motor, and why it was the predominant speed motor that we control the speed of, was for that exact reason. So a DC motor, the big advantage is we could easily control speed. Now, an AC motor, the problem we have with an AC motor is we can't control it with a current or with a voltage. So all we have to do on a DC motor, and so what we do is we have what we call an armature. It's got brushes on it. And then we got some type of field out here. This could be actually permanent magnets. And what we do is we create either a magnetic field out here or a permanent magnet field. So a lot of your little DC motors have permanent magnets in them. And then, or we could do an electrostatic motor, which gives us a lot more control. And what we would do is just change the voltage that we applied across the rotating part, which they call the armature. So all we had to do is change the voltage on the DC motor. The armature on the DC motor, the lower we made it, the slower it ran, the bigger we made it, the faster it ran. So very, very easy. Using the SCR drive, we can control them with bipolar transistors. I think I showed y'all the other night, we can control them with pulse width modulation, where we have a digital pulse that we put out to it. And then what we do is we change what we call the duty cycle. The smaller the duty cycle, the slower the motor runs. Very easy to control this. The problem we have with an AC motor wants to run at slightly less than what we call synchronous speed. So the RPM of an AC motor is set by 120 times the frequency divided by the number of magnetic poles. So if we had two magnetic poles, and these are always going to be electromagnets, well, this would be a north and a south, so that means we would have two. So we had a two-pole motor. We had a two-pole motor, and then RPM would be equal to 120, and we ran it at 60 hertz times the number of poles. This would be 2. So I'm going to bring up my calculator. It's up here somewhere. I'll clear this out. This is going to be 120 times the frequency. So this would be 60 cycles. 120 times the frequency equals that divided by the number of poles. So this would be a two-pole motor. And that would be 3,600 RPM. Now the motor can't run this fast because of something we call slip, but this is what it wants to run at. So normally we got two ways we can control the speed of a motor. We can change the frequency applied to it, or we can change the number of poles. So a 4-pole motor will run at 1,800 RPM. So what we're saying is if I increase the motors, and this, if you got a ceiling fan in your house, this is exactly what you're going to do. If you ever took the switch apart, it's got 3 leads on it. When you go from low to medium to high, you're selecting a different number of poles, which cause the motors to run at different speeds. But we very seldom control the speed of an AC motor, or you should never do that with the voltage. because remember, power on an AC motor varies with the square of the voltage. So if you raise the voltage up too high, the motor could burn up, it could tear stuff up, because now it's developing not more than the rated horsepower. If you try to run it too slow, remember the horsepower varies with the square. So that means you half the voltage, you're going to get 1/4 of the horsepower. Now the motor won't run, and it'll stall, and it'll burn up. So, and the problem we have with trying to vary it with frequency. So this is something we can vary electronically. So if I vary this electronically, then if I change the frequency, if I make the frequency goes up, it would appear that the motor will run faster. If I make the frequency go down, it appears that the motor will run slower. But the problem is we talked about this a little bit, we have something we call X of L. This would be the X of the L of the motor, which means 2 pi FL. So the motor has, the windings of the motor has a certain inductance. But if the frequency goes up, resistance goes up, current flow goes down. If current flow goes down, now the motor doesn't produce enough torque, and it stalls. And then it burns up if you don't protect it. If we lower the frequency, X of L goes down. X of L goes down, we're lowering the frequency, which means now the motor is going to pull a lot more current, and then we're going to burn it up. So what we don't do with an AC motor, a lot of people call them variable frequency drives, but they're not. They're actually variable speed drives. So what they do is they change two things. They change the frequency, and they also change the voltage proportionally. So that means if we raise the frequency, which causes X of L to go up, which would cause current to go down, well, if we raise voltage up by the same proportion, then the motor's going to keep running. Likewise, if we lower the frequency, what would happen, it would cause the current to go up unless we lowered the voltage. So I call these things variable speed drives, because what they're doing on an AC motor to control the speed is they're changing both the frequency and they're changing the voltage. If they only changed the frequency, they'd burn motors up all the time. So these are variable speed drives. Well, the problem is, how do I so this is the beauty of electronics, or this is the beauty of DC. So if you imagine, we could bring in DC or AC, then we can convert it back to DC. So this is AC over here. And then we could run it through something that they refer to as an oscillator, which converts it back to AC. But now I'm controlling this electronically. The problem with using just bipolar transistors operating in the linear region is motors are going to try to pull a lot of current. And the problem is we operate the transistor in the linear region, it acts like a rheostat. So it means the more voltage it drops, and we're pulling a lot of current, it's going to cause the heat to go up real high. So what we want to do is we want to operate these things as a switch. So if we switch them, then they're saturated, they drop almost no voltage. When we cut them off, then they conduct no current. So if we could come up with a method, I could use this to change my frequency. Well, we already understand pulse width modulation. So what happens, if I've got a certain pulses, and I do something like this, okay, understand. And then I can change this right here. This right here would change the voltage. Or I could spread them out, and I could use this to change the frequency. But what we're doing is we're going to be operating off a positive and negative voltage. So it gives me the ability to use pulse width modulation on an AC motor. And what your AC motor is going to do, it's going to see AC. It's going to round that off. So to do this, what we want to do is we want to operate switches. Okay, so I could use saturated switches. But what we want to do is we want to be able to reliably switch these things off at extremely high speed. We know if we saturate a transistor, we already talked about this. It takes a while to bring it out of it takes a while to bring it out of saturation because it builds up a charge. So what they did is they came up with a really, really neat invention, which we call, now remember, originally when the MOSFETs came out, these guys were referred to as insulated gate. field effect transistors, or what we call EFETs. And then over time, we started calling them MOSFETs. But what they came up with, and it'll show up better on another slide. So this is the way the book shows it, but I'm going to bring up another slide presentation. Okay, is what they've done is they've combined a MOS input because it switches easy. We exceed the threshold voltage. It's on the ease of switching and the speed of switching because it doesn't saturate, along with the power handling capabilities of a bipolar junction transistor. So what they came up with is they came up with an insulated gate bipolar transistor, which is basically a combination of it has a MOS transistor as the input, and then it's got a bipolar transistor as the output. So we got a MOS transistor feeding a bipolar transistor. And I'm going to pause this and bring up my other slide. Be right back. So this is the other slide. Got this off the internet here lately. So what they do on variable speed drives for AC motors is the predominant device used is what's called an IGBT. And it stands for insulated gate bipolar transistor. But we call them by their names. We just spread it out, IGBTs. And what they do is they combine an enhancement mode MOSFET because it has extremely good switching characteristics. It's very easy to control. We can fire that thing on. You know, we exceed the threshold voltage. It saturates. We can turn it off real fast with the power handling capabilities of a bipolar transistor. And we end up with this symbol right here. So this is the symbol of an IGBT, insulated gate bipolar transistor. And I don't know if you can see it or not. Here's the gate. Here's we create the channel. As soon as we create the channel, we put a base current into the base. The base saturates, and now we can come over here and do this. By the way, we're not going to go over this, but this emitter, we're using a PNP transistor, but it acts like an NPN transistor. So this is the actual symbol. This is what they're going to run into. So if you ever look at a schematic or do any research on these variable speed drives, you're going to see the driving device, the actual transistors that develop the pulse width modulation that runs these motors is going to be an insulated gate, but predominantly an insulated gate bipolar transistor. We still see bipolar transistors a lot. Sometimes we see what they refer to as power MOSFETs used a lot every once in a while, but they never ever can give you the drive, the power drive that a bipolar transistor can. So what they've done is they're using the best characteristics of both these devices to create these big power drive circuits. And the book shows you they come up here and get these things in modules. So they look a lot like this. This is high power. This is the symbol they showed y'all. So this is still called the gate. So the input is not called the base. So as soon as you see this split up right here, right there, it indicates this is an IGBT, right? The input of this guy is not called the base. It's called the gate. And then we don't actually see the other parts of the enhancement mode MOSFET. What we see is what appears a logical emitter and I guess you'd call it virtual emitter and collector. So this guy up here is called the collector. So this is where we'd put our big positive at up here. This right here is where the negative would go. I'm not sure if they do these common emitter. I don't know I'm sure if they don't do these common collector or a common emitter. I don't know exactly where they connect the loads at on these things. I'll probably try to do a little more research. You know, if I find out, I'll let you know at the next class because they hook up. They usually come in modules like this, which makes it real easy to control and real easy to troubleshoot. And then, and these guys here can handle extremely high powered loads. So here we have a real high input impedance on the gate, which means the devices that are controlling these things These enhancement mode MOSFETs, their biggest advantage, of course, is ease of switching, acting them like a switch. The biggest advantage of bipolar transistors is the amount of power they can handle. Because when we saturate those guys, the actual junction goes down to less than a volt, right? You saturate an FET, you still have the resistance of the channel, of the semiconductor material. So that's the big advantage. So IGBTs, these guys are used in what? Well, they're used in variable speed AC drives. What we're going to be looking at next, I'll have to find it in the textbook. Like I said, I didn't bring my textbook. But what we're going to be looking at next is what we call thyristors. And some of the thyristors we're going to look at is SCRs, silicon control rectifiers, and we're going to look at triacs. And we'll see what they do. I think they also consider a UJT to be there. We might look at those. We're going to probably look at diacs. And I can't remember if there's any more, but these guys all fall under the category of what we call thyristors. So if you want to do a little research on that, that would be fine. Now remember, this is going to conclude the lecture on FETs. You need to get your questions together for me, and we'll start off with a question and answer period at the start of class. You need to make sure, remember, you need to bring in your notes. That's what you're going to do to get credit for this lecture, is to bring in your notes. And by the way, if you have any questions, you need to put them in those notes so you can ask them. If anything comes up, try to remind me what we're going to talk about. I think we said I was going to show y'all some of the static safety things that we use when we deal with MOS transistors or MOS circuits. And anything else you can think of, just drop me a note, or I'll be looking at my email. Now I'm going to be in meetings all next week. In fact, sometimes we're going to be in other buildings. We're looking, by the way, at trying to be certified to offer a meter certification, and we'll see about trying to get y'all guys into that. So that'll give you some type of certification that you can put on your resume before y'all leave here. I'll talk to Nancy next week and see what we need to get the people in the program. We're planning on putting it into EET 100 and get people a meter certification right out of the EET 100 or Intro to Engineering. But I think we ought to try to get some way that we can offer that certification to you guys. I'll find out if it costs any money or anything like that. As soon as I find out, I wish I could tell you now, but I don't know. But as soon as I find out anything, questions on that, I'll inform you. We're supposed to go to our training on Monday morning. All right. Hope y'all have a great Thanksgiving. Stay out of trouble, and I'll see y'all Monday after Thanksgiving.